Let me thank Woz again for the introduction, for giving me his microphone. Thank you all for coming. So it's a great pleasure to be here, a great pleasure to give one of these public lectures of the special year. Actually, the public lectures are planned so that they will keep improving during the year. So no matter what you think about this lecture, you are encouraged to come to the next ones by Jennifer Chase and Jacob Fox and Dan Spielman. I'll talk about graph coloring, local and global. And let me start just by setting the notation. So my graphs will be finite and undirected. And I always denote a graph by a pair, VE. V is a set of vertices, E is a set of edges. And the vertex coloring of a graph is just an assignment of colors to the vertices of the graph. And it is called proper if adjacent vertices get distinct colors. So what you see here is a proper coloring of the graph here. Every pair of adjacent vertices get distinct colors. Now the chromatic number of a graph, G, is noted usually by chi of G. So this is the minimum number of colors so that there exists a proper coloring of the graph with that many colors. And I wrote here that the study of graph coloring is by far the most popular subject in graph theory. And it is motivated by lots of applications, most notably the investigation of scheduling problems. Usually when you prepare a PowerPoint lecture, you want a picture, you go to Google Images and you write. So I wrote here maybe applications of graph coloring, and I got this picture, and actually it's a nice example of a scheduling problem, but let me not elaborate on this. Here is another reason for the popularity of graph coloring, and this is the investigation of the best known problem, now theorem, in graph theory. And this is a four-color problem, or the four-color theorem, that says that every planar graph is four-colorable. This was conjectured by Francis Guthrie in 1852 and was proved by Appel and Haken with some help by Koch in 1976, and reproved again by Robertson, Sanders, Seymour, and Thomas 20 years later. And as probably most of you know, the proofs still make heavy use of computers, and there is no known proof which does not, so more traditional, which does not use computers. And this again a reason for studying graph coloring. Is another proof of the popularity of graph coloring. I just checked. This is not fully updated. It's from last week. Maybe it's changed since then. So in Math.net, there are 2,666 papers with the word graph coloring in the title. And there are actually 1,693 more with the word chromatic number in the title. If you go just to Google and write the same words, then it will increase by a factor of 100, roughly, these numbers. So it means that indeed graph coloring has been studied intensively. Now, because of the applications, it seems interesting to try to find ways to compute or approximate the chromatic number of a given graph, the minimum number of colors we need in order to color the vertices so that adjacent vertices get distinct colors. And in one sentence, what I wrote here is just the algorithmic problem of computing or approximating the chromatic number of a graph is hard. So there is some evidence for that, and also the best algorithms that we know for it show that it's hard in the sense that we've not been very successful. So let me tell you briefly about that. I'll not talk much about complexity classes, but I'll just state the results. So one of the early problems that is known to be NP-complete or NP-hard, this was proved by Barry Johnson and Stockmeyer in the 70s, and this is that even deciding if a graph is 3 colorable, and if the chromatic number of it is at most 3, this is an NP-hard problem. So this is the problem that we believe that is hard. And a modest improvement says something about approximation. So this is by Khanna, Lineal, and Safra. It says that even distinguishing between graphs with chromatic number 3 and graphs with chromatic number 5 or more, this is also difficult. Namely, the problem of coloring a 3-colorable graph by 4 colors, coloring it properly, this is still NP-hard. Now, if we are willing to assume some more, maybe less traditional assumptions about complexity classes, so we all, or most people believe that P and NP differ, maybe many people also believe some variants of the unique games conjecture. As I said, I'm not going to say much about complexity classes, so let me just assume that we know what this is, and if not, just think about it, that this is some hardness results that we believe in. So then it is known that for any constant C, then given a 3-colorable graph, coloring it by C colors is still hard, unique games variant hard. So at least as hard as some other problems that we believe that they are hard, in the sense that we don't know any efficient algorithms to solve them. Now, what do we know about algorithms? So let me say something about coloring 3-colorable graphs. Suppose we have a graph on N vertices, and suppose its chromatic number is 3, and we want to find in polynomial time a proper coloring of it using the smallest number of colors that we can. Knowing that the graph is 3 colorable, well, the best known algorithm does it by a little bit less than n to the 1/5 number of colors. So about n to the 0.2. This is due to Kawarabayashi and Fora. And this is in the end of a long list of earlier results by several people. And I should say that many of these algorithms, they use many interesting and nice ideas. So combinatorial ideas, and then geometric ones, if you want. So the use of semi-definite programming, then the use of hierarchies, and again, it's not so crucial to know what exactly they mean, but it means that some sophisticated tools have been used here, and then again, some more sophisticated combinatorial ideas. But despite all these ideas, I want to stress that the result is basically pathetic, right? So the graph is 3 colorables, namely it is possible to color it in principle by 3 colors, and in polynomial time the only thing we can do after all this work is to color it by about n to the 0.2 number of colors. Now the situation is even more pathetic if we don't look at 3 colorable graphs, but we look in general graphs, and we ask how well can we approximate the chromatic number. So there is a general result by Holderson, And it says that there is a polynomial time algorithm that approximates the chromatic number of an n vertex graph within a factor of roughly n over log cube n, so up to some log factors. Now you see, even before looking at the graph, we know that the chromatic number is some number between 1 and n, right? So a factor of n is without looking at the graph, without doing anything. And then if we make quite a lot of efforts, then we gain a factor of log cube n, which again is not much, but again this uses some clever ideas. What about hardness here? So Zuckerman basically de-randomizing some idea of Feige and Kilian, which is based on earlier work by Hastad, says that for any fixed epsilon, so epsilon could be 0.001, then it is NP hard to distinguish between or to approximate the chromatic number of a graph up to of an n vertex graph up to a factor of n to the 1 minus epsilon. So it's hard to distinguish between graphs with chromatic number n to the epsilon and graphs with chromatic number n to the 1 minus epsilon. Now we know that in the situation of lower bounds, we basically don't know to prove lower bounds for the complexity of natural computational problems. Natural, I mean, say, NP problems that belong to the complexity class NP. There are basically no lower bounds. So the only lower bounds are relative. Namely, we can say that if something, if P and NP differ, or if some problems are difficult, then also approximating the chromatic number is difficult. Or we can say that some things are hard to do in some restricted algorithms. If we don't allow the algorithms to do anything, but we allow them to do only some specific things. So here I wrote one example. This is from an old paper with Ravi Bupana, following the work of Rosborough. And it's not formulated there this way, but it follows easily from what is written there. And this is that if we want to write a monotone Boolean circuit that will distinguish between graphs that have chromatic number at least n over log to the 4n, let's say, and graphs that have chromatic number at most log cube n, so really this corresponds to approximating it up to n over polylog, up to n over log to the 7n, then this monotone circuit cannot have polynomial size. It must have size at least n to the log n. So, so this is if we allow only circuits that are allowed to do only n de Novo. But if we allow general circuits, right, so if instead of monotone it would have been written here general Boolean circuits, this would have been stronger than proving that P is not equal to NP. But you see, this is a monotone problem. So basically, there is a monotone circuit that if it gets as input a graph with chromatic number at least n over log to the 4n, then it outputs 1. And if it gets a graph of chromatic number at most log to the cube n, it outputs 0. But every monotone circuit like this should be big. Okay. So, so these are all things that should convince us that computing or approximating the chromatic number of a graph is complicated. And I think that one reason for this is the global nature of graph calling. Namely, the reason that the chromatic number of a graph is big is not local. We cannot see, or we cannot necessarily see some small witness that tells us that the chromatic number is large. Somehow intuitively or naively, when we first hear the definition of chromatic number, the easiest reason for a graph to have a large chromatic number is to have a big clique. If we have 10 vertices and each pair of them is connected, then the chromatic number is at least 10. Right? But the thing is that the chromatic number can be big although the graph does not have any clique of size more than 2. So it doesn't even have triangles. And this means that a chromatic number is global. We have to look at the whole graph to know something about the chromatic number, or even to approximate it. And this is something that makes it difficult. And indeed, what I wrote here is that there are graphs of arbitrarily high chromatic number containing no triangles. This is not a difficult result, but before you see it, then somehow maybe it's not the first thing we would think about. So here is an example. This is what is called the Grech graph. So this is a smallest graph of a chromatic number 4, and which does not have triangles. Okay? It has 11 vertices, and it has chromatic number 4. Now, so the first proof, or really observation, that there are graphs of arbitrarily high chromatic number which do not contain triangles, this was first proved by Tat in 1947, and it appeared in Eureka, which is a journal edited by students in Cambridge, England. And this appears in a pseudonym, Blanche Descartes, and actually a similar version by the same author appeared later in the monthly. Mentioning Blanche Descartes, let me tell you that she got her name from the initials of the first names of Tat, Brooks, Stone, and Smith. They were together undergraduate students in Trinity College in Cambridge. You see here pictures of all of them. So the B is Bill Tat, the L is from Leonard Brooks, A is from Arthur Stone, and C is from Cedric Smith. So this gave Blanche, and then she got her last name because of the common phrase carte blanche. And they wrote actually several papers together as Blanche Descartes, and then they wrote some papers also with their real names. Their best known paper is about squaring the square, namely they study the problem of taking a square and partitioning it into subsquares, no two of which are of the same size. It's quite surprising that this can be done, and they have a way of generating such partitions. This appeared in Duke in 1940. So this is about Blanche Descartes. And what I wrote here, and also in the abstract, is it's a study of graphs with a high chromatic number and no short cycles. So this is even more than triangle-free. So this had a profound influence on graph theory and combinatorics, not only in terms of results, but also in terms of methods. And I'll tell you a little bit about that. So let me talk about chromatic number in Girth. Here are the notations or definitions again. So our graphs are finite, undirected. We denote always a graph G by a pair, VE. V is the set of vertices, E is the set of edges. Chi of G is the chromatic number of the graph G. And then we denote by little g of capital G. This will be the girth of the graph, namely the length of the shortest cycle of the graph. Okay. And also we'll look sometimes at odd girth. So the odd girth of the graph is the length of the shortest odd cycle. You see, if the odd girth of a graph is big, then it means that locally it looks as if the graph is too colorable, is bipartite. Because if we look at a vertex and we look at the neighborhood, its neighbors and their neighbors and their neighbors and so on, if there is no short odd cycle, then for a while we never see any odd cycle, and it means that two colors suffice. but still maybe the global chromatic number can be large. So this is just a notation, and to practice it, here is a Peterson graph. So you see in the picture a proper coloring it by 3 colors. And of course, the chromatic number of it is at least 3 because it contains an odd cycle. It contains a cycle of N5. And so the chromatic number is 3. The Girth is 5, right? This does not contain triangles and does not contain cycles of N4. And the odd Girth is also 5. Okay. So let me say something about the history. I already mentioned that Tat or Blanche Descartes in the late 40s showed that for every k, there exists a graph G with chromatic number at least k and no triangles, namely Girth at least 4. In fact, his construction gave Girth 6. So no triangles, no cycles of N4, no cycles of N5, but in it's a recursive construction. We can make the chromatic number as large as we want. A similar construction was found by Kelly and Kelly. Actually, as I said, this Tat or Blanche Descartes published the same result in the monthly in the 50s. It appeared as a problem. It was asked by Peter Ungar, and the ones who solved it were Ungar and well, the one who posed it, and then Kelly and also Tat. Then there is another construction by Zykov. It's slightly different. Namely, it gives Girth only 4 and not 6, but arbitrarily high chromatic number. That's also a pretty famous paper, and one reason for this is that whenever it appears in the references of any paper or book, it is always the last one in the list. You see, ZY is hard to beat. So this is okay, and then there is another construction by Michalski. Actually, if we apply this Michalski construction, the first graph that we will get is the Grech graph that I mentioned earlier. And then the breakthrough was the result of Erdős from 59, which can be viewed as maybe first serious application of the probabilistic method in combinatorics. And he proved that for every k and for every g, there is a graph with chromatic number at least k and with Girth at least g. So no short cycles, not only odd, no short cycles at all, and still the chromatic number is big. Now for big chromatic number and triangle free, so just Girth bigger than 3, people looked quite seriously at quantitative estimates. So we want to ask how large can the chromatic number be as a function of the number of vertices, and if we don't have triangles, and basically up to a constant factor. This was solved by Aita Semredi and by Jiankhan Kim, and the constant factors have been improved several times after that. So basically, the result there up to a constant factor is square root n over square root log n. We did try this, but it will appear later. And these are probabilistic constructions. There are explicit ones. The best known explicit construction gives chromatic number about n to the 1/3. So n vertices, no triangles, and chromatic number basically n to the 1/3. What about explicit constructions for high chromatic number in the high Girth? So non-explicitly, this theorem of Erdős basically told us everything, and but we want to see some constructions, and actually I'll show you later in the talk. I'll show you some new construction. So again, there have been many. There was some construction by Neshikri that gave Girth 8. As I said, this construction of Tat gave Girth 6. Then Lovas found some explicit construction that gave arbitrarily large Girth and arbitrarily large chromatic number. It's complicated. And there was a simpler, still complicated construction by Neshikri and Bredel. Then there is a simple to describe construction, but maybe harder to prove by Lubovsky, Phillips, and Sarnak, and by Margulis. These are the usual constructions of expanders. For those that heard about them, they also happen to have a high girth, and because of spectral properties, they have high chromatic number. And then there is another construction by Krish. All of those are kind of complicated to describe. And then for high chromatic number and high odd girth, no short odd cycles, that's easier, and there are many ways to do it, but maybe the nicest one is what is called Kneser graphs, and this is maybe the first, or one of the first applications of topological methods in combinatorics. This is due to Noga. So as I mentioned, the study of this problem of graphs with high chromatic number and high girth was interesting not only in terms of results, but also in terms of methods. So I mentioned that the proof of Lovaas is one of the earliest constructions or uses of topological methods in combinatorics. Then the result of Erdős is maybe the first serious application of probabilistic methods in combinatorics. There have been earlier ones, but they basically can be formulated in terms of counting, and in fact they have been historically formulated in terms of counting. The word probability did not appear explicitly there. And here, although by now this proof is simple to describe, it's maybe one page, still it uses probability. Then there are some spectral techniques using the connection between the eigenvalues of, say, JCC matrices of graphs and their structural properties, and specifically their chromatic number. And then there are tools from number theory. So these papers that I mentioned about expanders by Lubovsky, Phillips, and Sarnak, and Margulis. Then the main thing is to prove to bound the eigenvalues of the graph. And this is done by the so-called Ramanujan conjectures, that are pretty deep results in number theory. These were proved by Eichler in the 50s. And they say something about the number of ways an integer can be written as a sum of 4 squares of a certain form. So this enables us to compute some traces of some, so basically to estimate the eigenvalues of these graphs. So let me talk a little bit about high chromatic number and high odd girth. So I want to mention two things here, and then I'll talk about high chromatic number and high girth. So I want to basically mention two problems here that I think are interesting. Both of them are quantitative, and they have to do with high chromatic number and high odd girth. And so the first one will refer to bounds. What we want to ask is what is the maximum possible chromatic number of a graph on N vertices with odd girth that is bigger than 2r plus 1. Right? So no cycle, no odd cycle of length at most 2r plus 1. When r is 1, this is just triangle free. Right? So when r is 1, as I said, this was basically solved by Eichler-Kromes-Femeredi and by Kim. And there's the answer up to constant factor is square root n over square root log. And the constants have been improved. Maybe there is still a gap of about 4 between the upper and lower bound. Something like this. Now, what about bigger r? So it's easy to see that the chromatic number cannot be more than some constant n to the 1 over r plus 1. Somehow. So I have, you probably noticed by now that I have a copy of the slides there, but once something is written in small print, I'm not completely sure I can see it. Okay, so it's easy really to see that the chromatic number cannot be more than a constant n to the 1 over r plus 1. And with Omri ben Eliezer, we observed that's not difficult, that you can also get a log factor here, so it cannot be more than n over log n to the 1 over r plus 1. If you plug here r equals 1, then you get the correct result for the case of triangle free. but in terms of the lower bound, the known lower bound is pretty far. So there is a result of Krivlevich that says that there are graphs on N vertices with odd girth bigger than 2r plus 1, in which the chromatic number is up to a logarithmic factor, at least n to the 1 over 2r. And explicitly one can, so this is probabilistic, and then there is an explicit construction that comes close to that, but is a little bit worse, so it's n to the 1 over 2r plus 1. But you see that the exponent is different from the exponent in the upper bound. So actually, you can just the question of graphs with odd girth bigger than 2r plus 1 is equivalent to saying that for every vertex, if you look at the R neighborhood of it, you look at the neighbors and the neighbors of the neighbors and so on up to distance R from the vertex, then there every neighborhood is too colorable, right? You don't see an odd cycle. So you can change these and ask what happens if you have a graph on N vertices in which every R neighborhood is 3 colorable. So instead of 2, I want it to be 3 colorable. How large can the global chromatic number be? And then it is possible to show that really up to logarithmic factors, in that case, then the answer is really n to the 1 over r plus 1. And this suggests, and this strengthens some earlier estimates earlier, and this suggests the problem that is it true that the maximum possible chromatic number of an n vertex graph with odd girth bigger than 2r plus 1, is it up to logarithmic factors n to the 1 over r plus 1? So this is the case for r equals 1, and we don't know it for any other r, but maybe this is a reasonable guess. This is one thing that I wanted to mention about odd girth. Another one is a specific graph, so this will be a Cayley-Knesser type graph, that I think it will be interesting because it will require some new methods, I believe, to estimate well the chromatic number of this graph. And so this is the following Cayley graph, noted here by GMP. It's a Cayley graph of an elementary abelian 2 group. So you take binary vectors of length m. These are the vertices, 2 to the n vertices. And 2 of them are adjacent, even only if they are nearly antipodal, namely the Hamming distance between them is at least m minus t. Namely, they agree on at most t coordinates. Okay? So this means it's a 2 graphs because I want to look at the case where t is not big as a function of m. And there is some reason to insist that t square is at most n. Because then for this range, the so-called fractional chromatic number is constant. Namely, the reason that the chromatic number is big for such graphs is deeper. It doesn't follow from the independence number, but anyway, so we can define this graph, and it's not difficult to see that the odd girth of it is at least m over t, so it is big. And it's just because every 2 adjacent vertices are nearly antipodal, right? So if you start somewhere and you want to close an odd cycle, but you always go to a nearly antipodal point, you have to go quite a bit until you close an odd cycle. Right? So this is the reason why the odd girth is big. And the question is, what is the chromatic number of this graph? And one can show something, so it's not difficult to see that the chromatic number is at least t plus 2. Maybe this can be improved a little bit, and at most t squared. And somehow it will be interesting to understand what it is in between. So I only wrote a few lines about it. The lower bound follows, uses some topological argument, so it just is based on Borsuk-Ulam theorem. Basically, it is repeating the proof of Josh Green, which is a variant of a proof of Baran, which is a variant of a proof of Lovász. It's a Kneser graph, have high chromatic number. But actually, for these specific graphs, it works in a nicer way because they are Cayley graphs, they are symmetric. It's kind of, so it's really something that can be described in a few minutes, but I won't do it. And this gives a lower bound of t plus 2. It looks some work by Karim Di and David Ellis suggests that maybe this t plus 2 can be improved to around 2t minus a little bit, but still this is linear in t. And then there is an upper bound, and the upper bound follows either by some probabilistic argument or by some results about covering codes. And again, I will not describe it, but this gives something like t squared. And I should say that some of the natural way to color this graph is to insist that every color class is a subset of a Hamming ball of a radius that guarantees that every 2 points in it are pretty close to each other and therefore are not adjacent. This is the biggest independent set of the graph. And if we insist on coloring by such sets, then it can be shown by using some results in discrepancy theory that the number of colors we need will be quadratic. And the interesting question will be if, well, which of the bounds is closer to the truth. I still have about 15 minutes, and I want to tell you a little bit about high chromatic number and high Girth. And mostly I want to describe some new, very simple, I think, explicit construction, which is interesting, and that's in a paper with Kostotka, Reiniger, West, and Jew. So for this, we need one definition. We'll see a picture, a simple definition. This is a DRG graph. What do we mean by a DRG graph? So we have a complete DRE tree of some depth. I don't care what the depth is. And then from each leaf, we have R edges that I call back edges. Namely, they connect the leaf to some ancestors of it. Okay? And we also want the girth to be bigger than G. Okay? So here is a picture. This is a binary tree, if you want. So you can imagine that we have here a full binary tree. And from every leaf, we have some edge or R edges that go back to some ancestors. I guess that in this stage of the talk, you already realize that my PowerPoint skills are very limited. In fact, this will be the most sophisticated animation. Let me show it again. Okay, so we understand what is DRG graph. I mentioned it again when I use it. And then it turns out, so it's not clear a priori, but it turns out that these graphs exist. For every dr and g, then these DRG graphs, they actually exist. Okay? So this is some, so you can make what? Yeah, the depth can be, yeah, if the depth is big enough. And indeed, it's a good question, maybe you wanted to ask it, that how big can, so this will be digression, what is the minimum possible depth of such a graph? So, because the proof that they exist is some double induction, and the depth is pretty big. And in particular, let me just fix specifically 2-1G graph. So what is a 2-1G graph? I think I have a picture again. So a 2-1G graph is, we have this complete binary tree that goes to some depth. And then from each leaf, we have here one depth edge that goes to an ancestor. And we want the girth to be bigger than G. So only one parameter, G. And let me denote by H of G the minimum possible depth of this underlying tree of a 2-1G graph. You want to understand this quantity. And actually, it's not so difficult to compute it exactly for small values of G, and I've done so. So h of 1 is 1, h of 2 is 2, h of 3 is 3. Okay, what you see here. Up to h of 7, it is 13. For h of 7, you have to think a little bit, but this is not too difficult. And once I had these 7 values, so it's the beginning of a sequence, you go to this Encyclopedia of integer sequences of Sloan, and you put 7 numbers, and it tells you, it recognizes this sequence. I didn't cheat, by the way. I really knew only these numbers, so I didn't compute h of 8. And this is a Mantel 2-run sequence, so it is a floor of G squared over 4 plus 1, namely it's the minimum number of edges in a graph on G vertices that guarantees a triangle, but just by coincidence maybe, but it is. So we may wonder what happens for bigger G. And in particular, what about h of 16? I want the Girth to be bigger than 16. So if the formula would have been the same, it would have been 65, right? So it's not 65. I don't know what it is exactly, but the fact is that it's at least the following. So this is, let me just explain that this is a tower function is 2 to the 2 to the 2 to the 2. And then what you see in the brackets is how many times you have to take 2 to the 2 to the 2. So again, I don't know how many times, but more than 2 to the 2 to the 2 to the 18. So in particular, this number is strictly bigger than 65. And this is, right, so this is not, that's right. So I was going to say, so this is an exclamation mark, and not a factorial sign, but even with a factorial, and in fact, even with three factorials. Okay, so it's really a big number, and in fact, the result is, and that's pretty technical, so it takes some effort to prove that really this behaves like the Ackermann function. So the correct behavior of this h of g is at least the Ackermann function of log base 2 of g, maybe minus constant, and post Ackermann function of g plus constant. There is a way to change the problem a little bit so that it will be both upper and lower bounds the Ackermann function of log of g. So these are really big numbers. But okay, but this was a digression. I still want to show you one thing, namely how to use this DRG graph. So they are useful for several things, but I want to show you only one thing, how to use them to construct quickly graphs of high Girth and high chromatic numbers explicitly. And okay, so here is how we do it. We start with this, so we take one of these DRG graphs, and D is k, R is k plus 1, and G is 2G. So this is, okay, and the vertices of the graph will be all the vertices of the underlying tree besides the leaves. This will be all the vertices. So it's simple to understand what the vertices is. Now the edges will come from the leaves. Each leaf will just give us one edge. So from each leaf we'll get one edge, and I'm going to tell you how. Okay, so how? What is a leaf? A leaf naturally corresponds to a sequence leading from the root to the leaf. So it's a sequence x1 up to xm. M is the depth of the tree in k to the n. Right? So this is because the tree is a KRE tree. Actually, maybe it's better to look at a picture. So here is a leaf, and you see that to go to this leaf from the root, then we first go to the second, I'm counting from the left, let's say. So we go to the second child, and then we go to the first child, and then we go to the second, then we go to the third. That's why it's 2, 1, 2, 3. So this is how it corresponds to here. Now from each leaf, we have here k plus 1 back edges. So by the pigeonhole principle, at least two of them, so there are some two of them that lead to some vertices in locations ij. so that xi is equal to xj, because the possibilities to the to the different xp's are just k, and we have k plus 1 edges. And then we just take two of them that are equal, and we connect them as an edge. Okay, I have the picture here. So here is this leaf starting the path leading to it starts with 2, 1, 2, and maybe there are back edges that go to the root and to the vertex 2 levels down, and because the two 2's are equal, then these are equal, and this will be the edge. Right? So this leaf will contribute this edge, and we do the same for each leaf. And if we have many choices, we just choose one of them. Okay, so that's the whole description of the graph. Now, why does this graph have a high chromatic number? It's easy to describe, and it's kind of nice that the coloring leads us to the monochromatic edge. So suppose we try to color by k colors the vertices. So the vertices, remember, are just the vertices of the underlying tree. Okay. And then what we can do is that we can follow the colors from the root according to the coloring. So if this is color 2, we go to the second child. This is colored 1, we go to the first. This is color 2, we go to the second, and so on. And then we reach a leaf. Right? And then, just by the definition, so this leaf, the edge that it contributed is monochromatic, right? Because exactly it was an edge that connected two things for which the x values were the same, but the x values are the colors, because this is how we went, and they are connected. So that's why for any k coloring, there is a monochromatic edge, and therefore the chromatic number is bigger than k. And then the fact that the girth is big is obvious, right? Because every edge that we have here, each one of these red edges came from two green edges in our DRG graph. And so if we would have a short cycle of red edges, we would have a cycle of twice that length with green edges, but we assume that there is no such cycle. So that's the construction. And let me just finish and mention some problems that I basically mentioned already, but I want to just repeat them. So the first one was this quantitative question of what is the maximum possible chromatic number of a graph on n vertices in which the odd girth is bigger than 2r plus 1. Is it true that up to logarithmic factors, this behaves like n to the 1 over r plus 1? This is true for r equals 1. And it's true also if we modify the question a little bit. We don't know it in general. There was this a nice Knesser type Cayley graph. Is its chromatic number closer to a t or t square? I think it should be closer to t square. But it seems that at least the usual topological ways to get bounds of the chromatic number will not give more than linear. And of course, a problem that I started with, it would be nice to find a better efficient polynomial time, say either approximation algorithm for the chromatic number of the graph, or to prove some stronger hardness results. And we finish with these pictures. So this is a Gretsch graph, which I said is the smallest graph, which is triangle-free with chromatic number 4. And the other one is more symmetric. It's called the Klebsch